Okay, so let us start again. So, in this session we are going to discuss about the security concerns of machine learning hardware. Okay, so, once you implement this, it is good that you can create efficient hardware running on edge IoT devices, but it have some security concern as well. Okay. So, I will primarily cover various attack first. I mean, what are the kind of attack possible on the machine learning hardware, and then I will talk about the kind of protection techniques. This attack on this machine learning model is something is not myth, right? It is kind of reality, right? So, you can actually see lot of news. It's I mean, some of the news may be 4 years, 5 years old also, right? There are side channel attack target machine learning models, right? So, security in critical at the intersection of AI and 5G. Then you have say that this says that defending AI system from cyber attack has not been solved. So, these concerns are real, and there are already reported issues that people try to attack the ML models, right. So, if you try to categorize your all attacks, it is basically primarily I am talking about privacy attacks. So, you have this membership attack, membership inference attack, reconstruction attack, model extraction attack, and property inference attack. So, these are the 4 different kind of attacks possible. I will primarily focus on this model extraction attack, and then if you see the model extraction attack, it is basically as the name suggests, it is basically you are extracting the model, right. So, basically what is the motivation here in this model extraction attack and all? See this when you try to run this ML, how do you get this ML model, the trend model? Can you tell me what are the steps you have to do to get this training process done? What are the things you need?
Data, firstly data processing steps are there, so after that data splitting steps, tokenization parts are there.
Yes, yeah.
And thereafter sir, we go in for the training part,
Exactly.
iteration of epochs are carried out.
And you need hardware GPUs, right. So, as your friend mentioned, so you need data, and data is not free in this world, right. So, it is basically costly. So, availability of data is a concern, sometime it is not available to you, right. It may be sensitive data, say some patient information that that the hospital does not want to share with anybody, right. So, the data is first of all not available all the time, or it may be costly. If something is available, you have to buy with cost. And then there are a lot of data processing, as your friend mentioned, that also involve time and efforts, right. And then the training, and training needs a very costly GPUs, right. You have to pay money, either you purchase in maybe $35,000, $50,000 what Professor Mishra was saying, and purchase your own GPU, or you pay the cloud provider and use that. So, it is all involve cost, right. And then through entire process, what you effectively get, if you just think about the deep learning model or neural network models, what effectively you get? What is the trend model?
They are weights to it, sir.
Exactly. So, you kind of know that there are 10 layers, each layer has 4 nodes, 10 nodes and all. So, you know the kind of structure, how many nodes, it is kind of known to you. Only thing is through this training process, what it does, it goes those exact value of those weights, right, and biases. So, all the cost involved there is to get those values, right. Now, if somebody do some attack, right, you can think about this weights are now the cryptographic keys, right. Whatever the attack you have done for this AES key finding, I can do the same stuff on the ML model, and I can identify the weights. So, then I do not need the data, I do not need to pay for my data, I do not need to pay for my GPUs, I do not need any manpower to do the training or data processing, right. So, that is the kind of motivation of the attacker to attack the ML models, understood, right. So, this kind of model extraction attack. In model extraction attack, you have kind of 2 kind of categories. One is basically you exactly identify the weight and biases. It can be basically other like hyperparameters, then architecture, trend parameters, but primarily we will look into this, which is basically the weight and biases. An approximate model is basically you do not need to get the exact random biases, but somehow you kind of create another model which will behave similar, right. So, something like this. So, once you think about, and I am talking about attacking the ML model on the edge and IoT devices, and it can be done through software or you can actually do through hardware, right. So, I am mostly focused on this. So, this is my kind of line of discussion, right. So, once you think about that ML hardware which is running on ML this in a edge or IoT devices, you can again do the side channel attack which I spent time in the first half talked about that, or you can also do the scan chain attack. I will talk about both, right. So, in this kind of talk I will briefly talk about the other attacks. I will not go into detail of them how it is being done and all, but I am primarily focused on this, and this is basically the most important one, and in that also I will primarily talk about when it is being run on a devices like IoT and edge, how this attack is possible, right. This is the kind of plan for the talk. Okay. Any questions here? Understood? This is the protection I will talk about later. So, the first one I was talking about is membership inference attack, right. This is something interesting. So, it is basically try to see that where a particular data was used in the training process or not, right. So, you have some data, say for example, you want to check whether that particular particular industry use your data, your medical data, right, whether you have used their all your whatever the reports you have done, all the data is with the company, whether you just want to check whether they have used your data or not, right. So, that is inference attack. So, in some cases suppose you have not given the permission that you do not use my data for your training purposes, but still they have used, right. How do you guarantee that they have not used, right. So, it is basically membership inference attack is that it is basically attacker prediction vector, and it is basically clinical record was used for train a model or not, right. So, this is whether they have violated the kind of agreement, right. In general, this is the kind of architecture for that. What you did that you have the model which is running in some say IoT devices or cloud everywhere, right. It is a black box to you. You do not know any information about that. What you do, you can actually query with your any data, right. You can always do the inference, and that is what is called shadow. You get some prediction also, right, for that data, that this. So, what it does is basically think about that you have some say some test report, you say whether there is a cancerous things or it is a benign, right. So, some such kind of things, or you have thyroids or not, so something like this, right. So, you have those data and it will give you the kind of predictions, right. So, you can take that model running on IoT devices or edge devices or in cloud, you create set of data set, you can run for 10,000 cases, right, who stops you, and you create data set, right, you create some k data set and you break it into training set and test set, right, 80-20, 90-10 whatever it is, and you create some shadow model, right, on this data set, because this is your data set now. And then you have this k such shadow models, and then you basically say if it is part of this you just add this output in the data, you augment with this data set in and out. If it is part of the your training, then it is basically in, if it is not part of the training, then you say out, right. This is how you basically augment this in and out your data set, and this entire thing you use for train another ML model. This is your attack model, right. So, what you will basically do this, it will now predict whether a data was in or out of a so, if you give any data now in this model, it will your output will be the classification in and out, right. So, whether that particular data was used in your training process or not, right. So, then you take this attack model, you now take this some data, you give it to this cloud or IoT devices, it will give you the prediction, you add this level and this, and it will give you whether it is part of training data set or not, right. This is the kind of model you can create, and which you can with that you can actually check whether this particular data part of this target model or not, right. This is the kind of overview of this membership inference attack. Okay. you can also have reconstruction attack, which is basically suppose you have a blurred picture, right. So, you have basically a blurred picture, you do not have the exact picture, you try to reconstruct back the original picture. Say for example, you do not have the original data, you want to convert into the correct the recovered actual images, right. So, it is basically use generative adversarial network, where they use this blurred data and create this model and try to get the recovered data, right. This is another kind of attack, reconstruction attack, where you reconstruct the original image from a blurred image. Understood? You can also have this property inference attack, which is another interesting attack, which is basically happening during federated learning, federated mode of training process. Say you have one server, you want to create the ML model, but you do not have the data with you. What you do in that time, right? So, you do not have data with you, but you want to create the model, but the data with somebody else, right. So, suppose this guy has some data, this guy has some data, and this guy also have some data, right. So, what you basically decided that I will create the model structure, I will give it to this guy, he will train on his data and he will give you the trained model to you. Everybody basically take the model, train it here and give you back the trained model, right, and you combine them together, right. So, you get model from model 1 from here, model 2 from here, model 3, and there is a kind of, there are many ways you can aggregate these models. It is kind of combine the weights, right, and maybe take an average of the weights to get the combined model. So, this is kind of very well known structure, where you don't own the data, but you still want to create the model, right. So, this is kind of federated learning model. So, these people does not want to give you the data, but he is agreed to you that I can train the model on my data and can give the trained model, right. So, he basically still can say protect his data, but still the training process can happen, right. So, now in here in this kind of federated learning process, somebody is adversary, the attacker, right. He also say ki, oh, I will also help you in this process of training, right. But his objective is something to get some other information from the others data, right. So, that is the kind of his objective, he will help you see what he is getting. So, he is getting, say suppose this process is happening for say 20 iterations. So, every iteration he is getting a trained model, and that trained model has some impact of the data of this guy and this guy, right, other participant, and he can actually compare the first version, second version, third version and all, right. So, he has all these version with him, and he can actually do some kind of analysis on that models, different versions of the model, and from there he can actually identify certain property about the data of this, right. To give some example, that say suppose you try to create the model to identify the gender of an image, right. I give you an image, you will say it is male, if I give her image, you will say it is a female and so on, right. But this guy want to see whether they are using the glasses or not. Suppose this is a company who want to sell spectacle, right. So, they try to identify how many of the data, this may be this company's total data. So, the employees, he identify how many people want to is wearing glasses there, so that they can connect these people and try to sell the maybe spectacle to them, right. So, this is the kind of an example, that although the final model is creating for say gender selection decision, that whether a particular image is of a male or female, he try to create a model that will also identify whether a particular person is wearing glasses or not, right. This is the kind of property inference attack in a federated learning mode. Any question here? Okay. So, these are the other possibilities, but as I mentioned, my objective is to give more detail into this model extraction attack, where I want to get either some hyperparameters like what is the batch size optimization algorithm being used, or the architecture means number of layers, layer type, or the number what is kind of kernel is used. But the most popular one is the trained parameter, that basically the weights and biases of the neural network, right. This is the kind of more important attack. Okay. So, this something that I have already explained. So, basically this neural network has all these different layers, and each layer has neurons, and it is basically if it is a fully connected, this value will go here, this value will go here, this value will go here, and every this edge has some weight, right. This is maybe W11, this is W12, this is W13, and suppose this is the value x1, right, this is x2, this is x3, So, basically it is happening xi into wi summation in this node, and then you are doing some activation function, it may be ReLU or other kind of activation, and then you will give the output, right. So, this is what is happening in each node, right, this is everybody knows. So, through the train process this value of this W11, W12 these things is being decided. So, extraction attack try to get these values, right, these weights. Okay. So, that I have already explained. Either it can be done with side channel or scan chain. So, side channel attack I have already talked about the power side channel. So, again I will show you how power side channel attack is possible on neural network hardware. Okay. I will give you walk through that process, and then I will talk about some countermeasures. So, this is the diagram I have shown earlier also, that basically you have some cryptographic devices running there. You can control the inputs and you can control see the waveforms power, you get the power, and from this analysis of the power you can actually see the cryptographic keys, right. So, in the neural network framework instead of the cryptographic keys here you are actually the neural model is running, right, that is the difference. And you can do the same process, you can control the inputs, you can control the inputs, and you can actually get the power, and you can correlate and you can get the weights. Okay. So, that is all, this is more detail. So, before going into the attack, in general in IoT or edge devices I already talked about the quantization, right. So, once you make your weights basically binary, then it is basically called binarized neural network or BNN, right. So, effectively you have this value W1 is basically 1 or 0, 1 means you multiply and otherwise you do minus 1, right. So, either you sum or subtract, okay. And this is basically to reduce the weight, right. So, it is basically in each node you are doing Wi xi, your all inputs are coming from the previous node and you are multiply with Wi and xi, but your value of the Wi is basically either 1 or 0, and 1 means you add and 0 means subtract, right, that is what is happening. And then this activation function is ReLU, it is basically if the summation is 0, if it is less than 0 then the output will be 0, or it is greater than 0 the value will be 1, right, this is what the ReLU does. And then finally, you have the max pooling function, which will just calculate the max of all these values, and that will give you the classification, right. Understood? This everybody understood, only difference with the neural network is that this Wi, the weights are basically binary here, and what is my objective? I want to get this value of Wi in the entire network, right, that is my objective. Any questions so far? Understood? So, how do you implement this node effectively this neural network? It is effectively summing these values, right, all these values Wi xi, right, W is either plus 1 or minus 1, I basically sum or subtract. So, you can actually create a adder tree, right. So, if you think about that there are 784 inputs. So, you have these inputs and you basically do the summation of two values, there will be 784 by 2 number of adder in the first layer, and you will get 396 values that you store in some register. Then you will have half of 3 for 96 adder in this, you will get 196 values and so on. Everybody understand this implementation? Anybody who do not understand this, how this actually the behavior of the node will be implemented in this node, this adder tree? Everybody able to follow this? Yes? Okay. So, this is quite straightforward, right. You basically have a pipeline design, you have one level of register here, you do the first level of summation, then the second level, and the final sum will come here, right. And where the attack will be mounted? These registers, right, these registers. Whatever the register, I try to see the power consumptions on a particular register, so that I can identify what is, because this value is what Wi into xi, right. So, either it, I know xi because xi I am giving, you do not know whether it is getting adding or subtracted, right, that is what you want to know. So, I can actually observe the power here and then I can figure it out whether it is these two value getting added or subtracted, right. Only thing is that I do not have access to this value. If I have the access to the value, I can directly tell whether this is addition or subtraction, right. To give you more idea is if you access to these values, say suppose you are giving here 5 and 3, right. If this weight is say I know this weight, so this is minus 3 say plus 3, so the value will be 2, right. So, if I get the value 2 here, I will definitely know that the W1 is minus 1 and W it is basically 0, that is why it is minus 1, and W2 is basically 1, that is why it is happening. So, if you have access to this value, the attack is straightforward, right. But in the power side channel, as you mentioned, that we do not have access to the value, but I can measure the power at this point say. So, what I will do? I will effectively do it for multiple time, right, and then I will see what is the change in power, right, what is the Hamming distance between the power. So, if you so as I mentioned that if you have this value is get summation, then the weights are 1 1, because if it is 5 plus 3 say, then it is 8, right. But if it is say 1 0, then it will be subtracted and so on. This you understood, right, based on the values that I already told you. So, it is very straightforward if you have the access to the values, but unfortunately you do not have access. So, what attacker will do? It will not run for only one cycle, it will run one cycle, it will observe the power, then second cycle will observe the power here, third cycle observe the power here, and if it is say getting summation, this will always follow the same pattern in this node, right, if it is say both are getting added. So, what I can do? I can see the Hamming distance between these two value, and usually Hamming distance is basically, you know what is Hamming distance? Is if you have two number, how many bit they differ, right. So, if it is say 1 0 1 0 and this is 1 0 0 0, what is the Hamming distance? 1, right, only one bit it differs, right. So, effectively and this is the toggle happen here, right. So, basically why I am calculating the Hamming distance, the power consumption as I mentioned earlier, how many time your value goes from 0 to 1 or 1 to 0. So, the power consumption is proportional to the Hamming distance, right. So, I can measure the power here, and based on the this power consumption, I can actually guess what is the Hamming distance between these values, and from there I can get the power. You got the idea, right? Do I need to clarify this again? Understood? Okay. So, this is how the attack will happen, and as deep you go, it will be much difficult. So, you will basically do this attack here first, then you will do the attack in this next layer and so on. This is how you are going to do that, so that you will be able to get all the weights. Okay. So, so that's basically the basic idea. So, this is how things being done. Now, solution is the masking, right. So, we have already discussed masking. So, we are going to implement masking on neural network, and we are going to use arithmetic masking, because your inputs may be integer, right, it is not binary masking. So, as I talked in the first half, that if you have arithmetic masking, so if you have a value x and if you want to create 3 shares, I am going to use 2 random R0 and R1, and my shares will be x minus R0, then R1 and R0 minus R1. This is my x0, this is x1 and this is x2. And the same convention, if you have access to the 2 value, you will not get the output. When you have access to the all values, you will get x, right. So, if you assume that I cannot access more than 2 location, then this particular solution will give you I mean it will protect your model from power side channel attack, right. So, if you can correlate the masking thing that I have talked about in the first half, this is straightforward, right. So, basically what I am going to do, I am going to break my weights into shares, and I am going to implement the entire things with shares, right. So, I can assume that I will basically have say 2 shares. Okay. So, then this is one adder tree, I will do. So, if you have 2 shares, then what will happen? It is basically if you have 2 shares, you will have x minus r 0 and r 0, right. So, you have one share is x minus r 0, this is share 1 and the other one is r 0. So, then I will do the entire thing for x minus r 0, the entire thing I will do for r 0, 2 shares, right. So, I will basically have 2 copies of the hardware, right. And then this is yeah. So, this is the original one and this is now break into 2 shares. Okay. So, basically you have kind of 2 copies of the adder tree because you have 2 shares, but there are few more interesting things happen here which I do not want to go that detail, but it basically says that if your value of this it basically says that if A is positive, A is that x I was talking about, then A minus r value is the chance of being A minus r become 50%, right. And if it is A is negative, A minus r will chance of becoming positive is 75%. The calculation I am skipping, but you can actually, it is very simple actually. So, suppose if this also positive, this also positive, right. So, and you are doing say A minus r, right, then there is a 50-50 chance, right. If A greater than r, then it will be positive, if it is not, then this, right. But if this is positive and this is negative and you are doing A minus r, this is definitely a negative number, right. So, this way you can calculate in which case what is the chance of the result is positive, negative, and you can take an average, this is 75%, this is 25%. So, what is a nutshell that from the probability of the value being positive or negative, I can actually make out whether the A was positive or negative, right. So, it is basically leaking information. So, that means sign bit actually getting leaked, right. So, effectively what is being done here, you calculate this sign bit separately, right. So, you do this adder tree for only the data, sign bit you calculate separately, okay. That is the idea, secretly. And then you remember that I am doing this summation because you need to combine these values. So, you again create a randomized version, here I am basically using LUT based implementation, I am not going into detail again, but this is kind of a safe or secure carry carry propagation implementation. So, that I can check whether the value is greater than or less than 0, right. So, this is basically for activation function ReLU, you have to check whether x greater than 0 or not, right. So, that can be done with this, okay. And then finally, you have to do the max pooling. In the max pooling, you have to take a max of these values, right. So, you have to compare 2 values, but I cannot combine these 2 shares, right. If you combine, then the value will be leaked, right. So, what I will do, I will not check this greater than this one or not, right. So, I will do what, I will just swap these values into this, so that I am not combining the share. Did you understand why the combining is a problem? If you combine these 2 share, the result will be A, and that is the secret to me, right. So, if you add these 2 share, then you will get A, but I do not want to do that. So, what I will do, I will not add them, rather I will just bring this here and I will bring that there. So, it is basically no summation, it is basically combine the shares of 2 different values. So, they will not reveal the data. So, this is basically a detailed discussion how you can actually implement masking on machine learning model, which is quite different from what I discussed in the first talk, right, where I talked about how we implement masking on cryptographic design, right. So, here to summarize, you need to implement this sign bit separately in the summations, because that is revealing something. For max pooling, you do not do the summation, then it will reveal A, rather you do this strategy. And for ReLU, you have this repeal carry thing, which actually can check whether x greater than 0. So, these are the detail of this implementation, through which you can create a masked version of machine learning model. Understood? So, that will be a safe solution, okay, where people cannot do the power side sensor attack to get the keys. Understood? Again, this is a future direction where I talked about that this masking has a lot of overhead. So, why not the transpose things, the circuit transformation I talked about, we can also implement the same thing in machine learning model as well. So, that will have a little less overhead as compared to the masking. Okay. So, that is a possibility. Everybody understand this, right? Okay. So, this side channel thing is done. Then I will talk about the scan chain attack on neural networks. Anybody know what is scan chain? Professor Mishra talked about this yesterday. What is scan chain?
So during manufacturing, sir, that time the scan chain is utilized to find out whether there are errors also.
Yes, exactly. So, it is basically to use for identifying manufacturing defect. So, if you have a circuit of say 1,000,000 transistors, if somewhere there is a manufacturing defect, as sir mentioned that there is a disjoint or there is a cross connection between two wires and all, your output won't come correctly, right. So, how do you identify or localize those things, that there is a manufacturing defect, you have to test it, right. So, to test it you need to get access of the internal data. So, which is not possible in the actual chip, because you only give input, you have the output. So, what test community come up with is this scan chain, right. In the scan chain what happened, whatever the register you have in your design, so their actual input is coming from the circuit, right. So, this is they say this is the circuit that is updating this register, right. For each register there are some circuit that is updating this register. But what I did, I just add a mux here and I connect one scan input in, scan in, and I put a mux here. This is the original input of this register, and this is the previous register input here, right. And this is basically scan enable, right. So, this is 0, this is 1, and for each circuit, for each register I did the same thing, that I just connect the original thing into 0 and previous register as 1 to this multiplexer, right. Then what will happen, whenever you give this scan enable equal to 0, what will happen? If I give scan enable to 0, what will happen? It will take the input from the circuit, because this will be 0 and this value will come here. So, this scan chain is disabled basically, right. That is called functional mode, where I give scan enable equal to 0, so that whatever the circuit interconnection, that will work, understood. On the other hand, if I give scan enable equal to 1, then what will happen? Which value will be selected here? This one, right. That means, whatever the outside value are giving, that value is going to store in this register, right. What will happen for this register? Whatever this output, that will go here, right. What will happen to this register? This value will go here, because this is 1. So, if I run it for 1 clock, what will happen? Whatever the input I will give, that will come here, right, and others will get some arbitrary values. So, to populate this register with my values, what I should do? So, suppose I want to set here 1, 0 and 0 here. So, I want to set this, so that I can check what is happening in this circuit, because if I know this is 1, I know this is a OR gate, I can see what should be the expected output, right. So, if I run it for 1 clock, I will give 0 here, and that 0 will store here, right. Next clock, I will make it again 1, I will give 0 again. Then what will happen? This 0 will move here and this 0 will come here, right. So, you will have 0, this is also 0, and this have some arbitrary value. Next clock, I will give 1, then what will happen? This 1 will come here, this 0 will move here, this 0 will move here. So, in 3 clocks, I can set whatever value I want to set to this registers externally, right. This is the purpose of scan chain. Now, see this, what is the, say suppose now sorry, I will just take about this. So, this is say NAND gate, right. Maybe I will clear it little bit. So, in 3 clock I disable the circuit and I set the value 100 to this register, right. Now, I want to check whether this is actually a NAND gate or not, right. So, say suppose I give here 00, this output is 0 and say this value is 1, right. So, this 1 will come here. So, what will be the output of an AND gate when it is 10? It will be NAND gate, it's opposite of AND, right? It will be 1. So, then this 1 should come here, right. So, what I am going to do is I know this value is 1. So, and this value is 0. So, this value should be 1, right. So, for 3 clock I make this scan enable equal to 1. So, that I set the value 1001. Next clock, 4th clock, I will do this scan enable equal to 0. Then what will happen? This value will now store here. It will erase whatever the value I write. But I know that because I know this structure, this value must be 1, right. So, whenever you put scan enable 0, now this will not take from the previous register, it will take from the circuit. So, now say this value becomes say 0, this value becomes 0, this value becomes say 1 because of these values, right. Next 3 clocks, this is basically 3 clocks, this is 4th clock, this is say 1 to 3 clocks, right. This is 4th clock, then again 5 to 7 clock. I will make this scan enable equal to again 1. Then what will happen? This value will go out from here, right. So, I will get first this 1, then I will get this 0, then I will get this 0. So, whatever value it was stored there, that will come out. Now, I can check that since this was a NAND gate here and I give value 0 0 here, this should be 1, but I got 1, right. It should be 1, but I got 0. When you get this value out from your scan chain, you can actually cross check what was the expected value and what you obtain. If they match, that means what? This was an AND gate, right. But if you got 0, that means the way this NAND gate is implemented in your circuit, there is some fault there. You will say that there are some fault in your chip, and in that is how you implement the NAND gate there. Did you get my point? How this scan chain actually help you to go internal detail of your circuit, and this is the kind of sequence of value which you can give scan input equal to 1 or scan 1 or 0. You got the point, right? So, this is basically scan chain, and it is being automatically inserted in any design by any software, right, because you have to test your chip. Okay. Now, in a machine learning model, when you implement, usually the output of this neuron gets stored in the registers, right. So, the output of this neuron where you are doing Wi into Xi plus checking the ReLU, that output goes stored in the registers. Okay. Now, when you do, if you send your chip to the testing facility and there may be some not dishonest people there, they can utilize it, this scan chain, and whatever I explained here using this same procedure, they will get the output of this node, right. So, they can exactly get the value what is output of each neuron, right, through the access of scan chain. Did you understand this? Yes, that because this scan chain have to add it to this, I mean this register will need to be there for say probably you add a latency layer here. So, there will be register there, and this register will be connected in scan chain for testing purposes, and the dishonest person utilize this and you will get this output. When you get this output, can you get W? Because you can control X, right, you are doing W in I into Xi. So, if you give say it can be binary or any network, say suppose you give X equal to 5 and your output you get 20, can you make what is W? What will be W? It is 4, basically it is Wi into Xi, right. So, same philosophy, what he will do, he will give all other values 0, only one value is some non-zero, and then it will basically get W1, because in that time only W1 will be stored there, other is multiple, see especially Wi into Xi, right. If you give Wi equal to Xi equal to 0, it is becomes 0, only one value is non-zero. So, this guy what will do, if there are 10 inputs, it put all 9 inputs 0, one value 1 and non-zero, maybe 1, 5 whatever it is, and it will get the value. From there he can make out what is the Wi, and he will do for each input. First it will give this value is non-zero, other 0, then it will give the second value non-zero, other 0, and this way he using scan chain he can actually get all the weights of your design, right. This is the scan chain attack. Okay. So, this is basically have detailed basically if suppose you want to attacking this node, we have example here. So, you give such a way that only this value is say non-zero, other are 0, right. So, you will get this value effectively. Then I make little bit value modification, because there is a ReLU operations, it is not the exactly WIYI, because there is some bias getting added, right. So, what I will do, I will now give say suppose I initially I give x, right. So, I give C1 as x, and then I will give Ci plus some value Ci plus 5, okay. And then you make a difference between these two, you will get exactly the difference, all this bias everything goes out and you will get the weights, right. So, in 2 iteration you can get that. Everybody understand this? The same thing I can do for other layer, but if you go further layer you have to do little bit more calculations, but it is possible, right. So, you can actually identify what is this value, and then I can use this to get these values, right, but it is all possible, it is all mathematics, right. And this is being demonstrated in this work recently, that with scan chain you can actually get your, it is much easier to attack, right, because in power side channel you are assuming that I do not have the access to these values, right, this output, but here because of scan chain I have access to these values, and it will be much easier, just some mathematical calculation equations you will solve it, you do not need any power side channel anything, just you control the inputs and it will give you the outputs. Okay. Any question? So, this is very powerful attack, right, it can break your weights very quickly, right. So far we have not seen much countermeasures, we propose couple of them, I will talk about that. So, how do you protect it, you say? I will not go into solution, let us see. You have this access to this point, right, scan chain, you cannot stop that because that is designed for test, right. How can I stop that? So, that means attacker still access this value, but still he cannot get the weights. What are the things I can do? Any suggestion? We come up with 2 suggestions, I will talk about that, but before that I want to you to propose something. Yeah.
Sir, one is that the access to the scan chain should be through some kind of authorization. Nobody else should be able to
yeah, understood, but basically you give the contact to some test facility, right. Some test facility is coming in Gujarat, sorry, in Guwahati now, right, and there may be some dishonest person there. So, you have an agreement that you test me and I authorize you to test, and one of the 200 people is not honest, right, he does this, right. So, this always happen, and this is because so many things get leaked and all, right. But what kind of modification I can do, so that even if I give you, you will not able to get. Shares is one thing I have talked about. Yeah, shares is one solution, that you now you get kind of random values, right. So, you will not get that. That is one of the solution, that protection whatever I talked about on this masking, that also kind of gives some protections, that is good. So, good solution. Any other solution? Lightweight masking is heavyweight solution, right. Can I have some lightweight solution? Anybody? It is a long day, some thoughts at the end of the day. Philosophy is that you still have the access at this point, but he will not get what weight is being used there. Can I obfuscate or hide the weight? Right. So, if he does not know whether it is a WI or this, he will not able to make out, right. Okay. So, maybe I will talk about the solution. Sorry, use the mic.
Like by encrypting the weights.
Encrypt the weights, okay. But if you encrypt, then your computations has to be also on the encrypted domain, right, that is homomorphic encryption or something.
Yeah.
So, you cannot do multiplication, right, because 5 is encrypted to 70.
Yeah, yes sir.
So, then the multiplication has to be done on encrypted data, so that is a different ballgame, right, but a good try, yeah. At least I got 2 solutions, which I not thought, I do not thought about, okay, good. Any other? We thought about 2 solutions, one is good, one is bad, and I got 2 solutions from here, which is good. Okay, let us move on. So, the first solution we talked about that. How about retrain the model with you add a key in your data set. Okay. Suppose you are basically having a 16-bit data input and output is some classification, say 0 of 2 bits, okay, and you train that neural network on this data set. What I am going to do it now, whatever the data, I will just add a 32-bit key here. Okay. So, your data set now become 48 bits, and then I retrain the model. I will get a different model now, not the same model, it will give a different weights and biases. Okay. And then when I sell this to the market, I will put this key into some tamper-proof memory which is inside the chip, okay. And then I will send it to the market. So, from the user perspective there is no key, right, they will still give the 16-bit input, they will get the 2-bit output. Okay. But when I give to the test, I will not give this. This is basically the final product, right. I will only give them to test this. So, since they do not know the key, they will augment some arbitrary key and that will be given there, and ideally the accuracy should be or the prediction should be incorrect, because your the key that you have added is not there. So, if you give a arbitrary key value, it will effectively not predict or classify correctly. Make sense? But this has a cost because you have to retrain again, right, and training process may takes time, right. So, this is one solution, but may not be very good solution. Without retraining, if you can do, that will be best, right. Understood? You understand how it will protecting the weights? Even if you get that, because your this data is not there, you get all incorrect. So, you cannot control your input. So, what you are doing, try to say that you are doing Wi into Xi, but the entire Xi is not available to you. So, you do not know what is Wi_Xi. So, from Wi_Xi you will not able to make out what is the Wi, because you do not know part of Xi, right. This Xi is now 32 bits, 32 plus 16, you have only access to this 16 bits, other 32 bits you do not have access. So, if you give something, you will not know what is the outcome, right. So, that is the kind of idea. Okay. So, this is one solution we thought of. The second one is interesting. What we did is basically we add few dummy nodes, okay, and we obfuscate these interconnections, right. We obfuscate these interconnections. We will not tell you whether this node is multiplying with this or this node is multiplying with this, and it is basically for not fully connected network. If it is fully connected, everything is getting multiplied, right. So, the idea is very simple, that I would add a mux here, multiplexer, and whatever the input node, I will connect all of them, and there is a key that will select the correct input, right. So, then there is this is Wi, right. So, I do not know which Xi will getting multiplied with Wi, right, and same thing in every process, and I use different key. So, here maybe the correct value is 0 0, here it may be 1 0, it is maybe 1 1 here, here may be 1 1. So, total key size become 2 bit 8 bits, and they will pick the correct values, right. So, now if you give this network, if you have access to this, because you are doing Wi into Xi, you are doing this, but you do not know which Xi is getting multiplied with which, right. So, you will not able to control which particular input 2 will give non-zero and other 0, right. So, it will basically you need kind of exponential try to give to identify the correlation. Understood? Clear? So, this we did, and this is what is our tool. If is basically if you give a train network, it will add this key and it will give you this obfuscation of these interconnections, and then if you use this HLS for ML or our LHS, it will give you the RTL, right. So, that you will get the RTL basically. So, we have some experiment that if you give wrong key, how it is impacting, and it is very interesting to see that if you have say this model we have used, there are 5 layers, actual accuracy was some 96%, and I have just used only say 8-bit key, okay. And if you lock the last layer, the 5th layer, if you just give 2-bit wrong, your accuracy becomes 62%. So, almost 35% drop in the accuracy, right. If you make 4 bit change, accuracy become 34, which is basically useless model, right. So, from 96 become 34. Similarly, whenever you have say 8 bit, if you lock the first layers, 2 bit only dropping is 1%, right. If you change 4 bits, dropping is only 4%. So, what it suggests? That you should lock the last layers, right, because in the last layer if you even lock 2 bits, I mean if you just give 2 wrong bit is 30% regression in the accuracy. Here it is only 1% or 3%, and this was consistent for every model we tried. So, the takeaway from this, that when you try to lock, you do not need to lock the entire model, you take the last layer and lock there, right. So, if you lock or obfuscate that layer, even if you give 1-2 bit also wrong key, your accuracy will be significantly drop and the model will be useless. And since during testing I will not give you the correct key, so it is basically useless model, you will not able to get anything. Your prediction is itself wrong, right. So, you will not able to use it. Okay, so, that is all, and we have shown that we did experiment, and we basically, so that because we are only adding 1 mux layer, 2 mux layer in the entire circuit, there is a lot of multiplier and all. So, obviously area overhead is insignificant, not even 1%, right, and it is just adding the delay of 1 multiplexer. So, delay is also very less, overhead is also less, not even 1%, right. So, it is a good solution effectively. Okay, so, that is this is basically on the solution we talked about. We basically this is one solution. The other one is that the future direction I was talking about, we are locking the network. So, there are lot of work in the research community, how do you lock this scan chain also. Okay. I mean it is well known that thread that through scan chain you can do many kind of attacks. So, there are many way you can actually lock the scan chain, and one of the recent work is called dishonest oracle. It basically says that whenever you try to access the scan chain in, it will basically give a wrong key, so that you will not basically get your correct scan chain, right. It will basically arbitrary values, right. So, as a result you can actually use scan chain in the functional mode or testing mode, only if you are authorized, then only you will be able to do that, right. So, basically just to give you the idea here is that if the scan enable, so there is a specific value, give it to scan enable, whenever it is giving 1, it will select this wrong key, right, and this is your lock design, or this one it will basically get wrong keys, right. That is basically a 2 layer protection, that you try to lock the scan chain as well as lock the design, and make sure that if you try to access my scan chain, it will give you wrong key, but testing will be still done, right. And then you might question me that how the testing will be done. I know that if this is the wrong key I give, what is the corresponding output. So, he do all this test and he will get the wrong key, not the correct key, because he will still get the weights, but that will be the wrong key, not the correct key, right. So, this is where my testing will be done, and I can stop that guy to get the correct keys, right. This is how the idea of this, but this can be done in future. Okay. So, in conclusion, in today's discussion we talked about various possible attacks on machine learning hardware, and then we talked about few solutions for both kind of this scan chain and power side channel attacks based solutions, right. One solution is basically the masking, but masking has lot of intricacies here, it is not straightforward application as we discussed. On the other hand, for scan chain you need to obfuscate the interconnections and also obfuscate the scan chain, and combining them will give the best solution. Okay. So, that is all for the day. Thank you. So, we will conclude here today, and tomorrow we will continue again from 10 a.m. Okay. Thank you.